Have you ever felt really stuck? Like there's a habit you just can't seem to break. Or maybe you've been feeling a bit anxious, perhaps, or down lately, and you just wish you could, I don't know, shift it somehow.
Yeah, that feeling is really common.
Well, what if you could literally change the very architecture of your brain to, well, transform your life?
It sounds almost like science fiction, doesn't it?
It really does. But it's not. It's the incredibly exciting core of what we're diving into today.
That's right. For a long time, the prevailing wisdom was that the brain you were born with was, well, largely the brain you were stuck with, fixed.
Right, sort of set in stone.
Exactly. But revolutionary neuroscience has fundamentally overturned that idea. We now know the brain isn't hardwired at all.
Okay.
Instead, it's profoundly soft-wired by, every single experience, every thought, even every action you take.
Wow, so it's constantly adapting.
Constantly. Which means the capacity to rewire parts of your brain isn't just possible. It's actually happening all the time, whether you realize it or not.
Okay, let's really unpack this then. Our mission today is to take a deep dive into how these fascinating developments in neuroscience, how they aren't just abstract concepts for scientists in labs somewhere, but really practical, actionable insights for you right here, right now.
Yeah, bringing it down to earth.
We're talking about tangible strategies, things you can actually do to improve, well, everything from your mood and memory
to relationships, even sleep quality.
Exactly. And our source material for this deep dive, it comes directly from Dr. John Arden's groundbreaking work in Rewire Your Brain.
A really foundational text in this area.
Absolutely. He masterfully translates this complex neuroscience into practical, applicable strategies for everyday life, things you can actually use.
And what's truly compelling here, I think, is that we'll be exploring the scientific basis for how intentional changes you make in your thought patterns and your behaviors, how they literally reshape your neural landscape, your brain's physical structure.
So it's not just about feeling better, although that's part of it.
Right, it's deeper than that. It's about enabling lasting, profound, personal transformation. And we're going to go into, significant detail today.
Yay.
Providing easy-to-understand explanations to help you grasp not just what happens in your brain, but crucially, how it happens and why it matters so profoundly for your daily experience. I want to make it really clear.
Fantastic. And just to give everyone a clear roadmap for this journey, we're going to start by challenging some of those outdated beliefs about the brain, the old paradigms.
Breaking down the myths.
Then we'll sort of embark on an exploration of its incredible architecture, from its vast hemispheres down to the individual neurons.
And those chemical messengers.
Right, the neurotransmitters.
Okay.
From there, we'll move into the actual mechanisms of how this rewiring process occurs. Neuroplasticity is a huge work.
A core concept, really.
And finally, we'll bring it all home. We'll talk about concrete, practical steps you can take to apply these principles directly to your own life.
Making it useful.
Exactly. So get ready, because you might just rethink everything you thought you knew about your own brain.
It's pretty mind-bending stuff, actually.
Okay, so for so long, this prevailing belief, it was really rooted in a sense of, biological destiny, wasn't it?
Absolutely. The idea that the brain you're born with is essentially the brain you're stuck with.
Yeah, and it was common thought, I remember, that the number of brain cells you had at birth was sort of your fixed maximum.
Like a quota you couldn't exceed.
And that your brain was hardwired to function in these very predetermined ways.
Right. You hear that term hardwired all the time, even now.
Think back to those widespread narratives, maybe through the 80s and 90s, about genetics rigidly predetermining everything.
Oh, yeah. The nature versus nurture debate leaned heavily towards nature back then.
Like those stories of identical twins raised apart who still had the same mannerisms or, like the same color shirt.
Exactly. Popular culture really grabbed onto those stories.
Yeah, saw them as solid evidence of genetic hardwiring, like an unchangeable blueprint.
And if we connect this to the bigger picture, this old view, well, it was incredibly limiting, wasn't it?
How so?
Well, it's quite disempowering, really. It implied a certain fatalism about our capabilities, our potential for growth.
Like, this is just how I am.
Precisely. If our genes dictated everything so rigidly, where would personal growth even fit in? Or therapy? Or the very idea of self-improvement?
That's a really good point.
It raises an important question for you to consider. If our brains were truly fixed, immutable from birth, how could we ever adapt to new situations?
Or learn new skills.
Or recover from life's challenges? This deterministic view just left too little room for the incredible adaptability and resilience we now know the brain possesses.
Okay, so thankfully the brain revolution has arrived.
Laugh softly.
Yeah.
Yes, the paradigm has shifted.
And neuroscientific research is now, well, overwhelmingly telling us the brain is far from fixed.
Far from it. It's incredibly plastic.
Plastic, that word seems key.
It is. It signifies a truly dynamic organ that is constantly being modified by your experiences throughout your entire life.
So it's not just a metaphor.
Not at all. It means your brain is physically changing all the time.
Wow.
And here's the really dramatic part. The bit that completely overturns that old belief about a fixed number of neurons.
Yeah.
New brain cells can actually be born throughout your life.
No way.
Really?
Yeah.
It's a process called neurogenesis. It happens.
That's incredible. So what about genes then? Don't they play a role?
Oh, they absolutely do. Genes certainly lay out potentials, vulnerabilities too. But here's the crucial distinction. They do not dictate your specific thoughts, your feelings, or your behavior.
So behavior isn't rigidly set.
Not at all. And get this, you can even turn genes on or off with your behavior.
Wait, what? My actions can change my genetic expression?
In a way, yes. Your actions, your environment, your choices influence which genes get activated or silenced. It's astonishing.
That leads into this nurtured nature idea, right?
Exactly. That concept is absolutely crucial. It fundamentally shifts our understanding.
Away from nature versus nurture?
Precisely. It means our experiences, our environment, our actions, our thoughts, they play a major active role in shaping our fundamental biological predispositions.
So we're actively sculpting our own biology, in a sense.
That's a great way to put it. It's about how we nurture nature, how our daily interactions and choices influence and activate our genetic blueprint.
Shaping who we become, how our brain functions.
Yes. This understanding tells us that our choices have profound, lasting effects on our neurological landscape. It's empowering.
So, okay, let's bring it back. What does this all mean for you, the listener?
Well, this fundamental shift in understanding the brain, it directly empowers your ability to maximize your potential and minimize those vulnerabilities we talked about.
How does that work in practice?
When you learn to intentionally rewire your brain, it directly leads to feeling calmer, more positive.
Which sound like pretty foundational states.
They really are. So much hinges on those two abilities. By learning to cultivate calm and positivity, you can dramatically improve your ability to focus, to face challenges head on, effectively reach your goals, and ultimately experience greater overall happiness and life satisfaction.
So it's about feeling less tense, maybe.
Less anxious.
Exactly. Less easily stressed in situations. Sure. Tend to overreact.
Adding needless stress.
Right. Understanding how to get those parts rewired, how to gently guide their responses, that's key to finding that inner calm.
And the flip side, feeling down.
Yes. Conversely, when you're feeling down, maybe losing your optimism, seeing the glass as half empty, you'll learn how to activate the parts of your brain that need to be, well, regulated and balanced.
You can intentionally boost your mood.
You can. You can learn to calm down in the face of stress and approach life with a more positive, resilient outlook. It's trainable.
Absolutely. So this deep dive into your brain's capacity for change, it really means feeling less tense, less anxious, less easily stressed. It means improving your memory, maybe cultivating better relationships, even getting a consistently good night's sleep.
Yeah. All of these are within your reach by understanding and actively utilizing your brain's incredible capacity to change.
It's not just abstract theory. It's a practical blueprint for a more vibrant, self-directed life.
Okay, so we've established this incredible adaptability. Let's zoom in now and really appreciate how this complex organ is, well, put together piece by fascinating pace.
The architecture, yes.
This 3-pound organ, it's just a marvel of biological engineering. It houses a staggering, 100 billion nerve cells.
100 billion neurons, yeah.
Yeah.
It's an astronomical number.
To give some perspective, that's roughly equivalent to the number of stars in our entire galaxy.
It really puts it in scale, doesn't it? And that's not even counting the many, many more support cells, the glial cells, that help them do their crucial work.
And it's not just a random jumble in there, right? They're organized.
Meticulously organized, actually, into what scientists call modules.
Modules? Okay.
These include things like the cortex, that's the highly wrinkled outer layer, which is divided into 2 distinct hemispheres. Then you have the 4 main lobes in each hemisphere.
Frontal, parietal.
Temporal, occipital, yes. And then a variety of subcortical modules located deeper within the brain, underneath the cortex itself.
Understanding these divisions helps us appreciate how functions are kind of specialized but still connected.
Exactly. Specialized yet intricately connected, creating this cohesive whole.
Okay, this brings us to something that gets talked about a lot, and maybe where we need to clear up some common misconceptions.
I think I know where you're going.
The famous left brain, right brain idea.
Chuckle softly. Yes. The pop psychology favorite.
You've probably heard the hype, right? It was really big back in the 70s, this idea that right brain people are inherently creative, intuitive.
While left brain people are rigid, logical, analytical.
Yeah. While that idea still floats around a lot in popular culture, the science has moved on, hasn't it?
Oh, definitely. Many of the scientists who initially explored hemispheric differences have long since abandoned such simplistic divisions.
So this raises an important question about these popular misconceptions.
Because while that 70s hype persists, the truth is the two hemispheres of your brain work together all the time. In everything you do.
Collaborating.
Constantly communicating, integrating information, collaborating. There's a crucial band of fibers called the corpus callosum.
Corpus callosum, okay.
Think of it like a massive superhighway connecting the two hemispheres. It serves to bind distant neurons that fire together, adding dimension and depth to everything you experience and think.
So without that constant crosstalk,
your perceptions and thoughts would be far less rich, far less integrated. It's vital.
Okay, so if it's not strictly creative versus logical, what are the general functions then?
Well, generally speaking, for most people, the right hemisphere is more involved in processing visual and spatial information.
Like seeing the layout of a room.
Exactly. It helps you grasp the big picture, paying more attention to the overall context or the gist of a situation. It also tends to be more active when you're learning something entirely new, something conceptual.
And the left?
Well, once that knowledge becomes routine, sort of overlearned, something you can do automatically, like maybe driving a familiar route, the left hemisphere typically takes over more. This side is generally more adept at details, categories, and linearly arranged information.
Like language.
Exactly like language,
Right.
which is processed primarily, though not exclusively, in the left hemisphere for most people.
Interesting. And you mentioned the right side is more connected to emotions.
Yes, it tends to make stronger connections with those subcortical parts of the brain that process emotions.
So it's better at picking up the mood?
It seems to be more attuned to emotional nuance, yeah. Better able to pick up the emotional climate of a conversation, for instance.
And there are differences between men and women here, too.
There appear to be some general tendencies, yes. Research indicates that, on average, women's brains may have better interhemispheric connection. The corpus callosum might be denser.
Meaning more communication between the sides?
Potentially, yes. Which could contribute to women often being perceived as perhaps more intuitive, or words maybe carrying more emotional weight for them.
Okay.
Also, women tend to show, on average, a greater density of neurons in parts of the temporal lobe involved in language, which might explain why verbal advantages sometimes appear earlier in life.
And they use the hippocampus differently for verbal tasks.
When developing verbal strategies, women often activate the left hippocampus, that memory center, more than men do. Men, conversely, often show greater visual and spatial skills and tend to activate their right hippocampus more during spatial tasks.
Fascinating. So subtle, but potentially significant differences.
Subtle, yes. And remember, these are averages, not deterministic rules for individuals, but they highlight the diverse ways we all process the world.
Okay, so beyond the hemispheres, each side has those four major lobes you mentioned.
Right. The frontal lobe at the front, the parietal lobe kind of in the middle, pop, the temporal lobe on the side, near your temples, and the occipital lobe at the very back.
And each has its specialty, but they all work together.
Always together. That example from Dr. Arden's work about appreciating a chair is perfect for this.
Remind us of that one.
Sure. Imagine you're at a friend's house admiring a really nice chair. The thoughts and feelings aren't just in one spot.
Okay.
You recall the elegant shape that's likely engaging your right parietal lobe, which handles spatial awareness.
Got it.
You remember the words your friend used describing their trip where they bought it? Maybe Costa Rica, that involves your left temporal lobe for language comprehension. You process the tone of their voice as they spoke. That's your right temporal lobe picking up emotional cues and sound.
Okay.
And as you leave, you glance back. Notice its deep cinnamon color. That's your occipital lobe at the back, processing the visual information.
Wow. So one simple experience, a whole brain event.
Exactly. It beautifully illustrates how integrated brain function really is. It's a symphony.
Okay, let's zoom in on one specific lobe that gets a lot of attention. The frontal lobe.
Ah, yes, the executive suite.
You call it the executive suite. I like that. It's the most recent addition, evolutionarily speaking.
Relatively, yes. And it's remarkably large in humans. Makes up about 20% of our brain.
Compared to what in, say, a cat?
A cat's frontal lobe is only about 3.5% of its brain. A huge difference.
And what's really crucial to understand, you mentioned, is that it's the last part of the human brain to fully mature.
That's right. Its development isn't fully completed until well into your third decade of life, usually mid-20s.
Which explains a few things about teenagers and young adults, maybe.
Chuckles. It certainly contributes to understanding impulse control and decision-making development, yes.
And specifically within the frontal lobe, there's the prefrontal cortex, the PFC.
Yes, the very front part.
Yeah.
This area provides us with our most complex cognitive, behavioral, and emotional capacities.
Like what kind of capacities?
It's what enables you to develop and act on a moral system, for instance. It allows you to set aside your immediate needs and reflect on the needs of others.
Empathy.
Empathy is a big part of it, yes. It's crucial for that.
So damage to the PFC would be pretty serious.
Extremely. A person with significant PFC damage might engage in antisocial, impulsive behaviors, or conversely, show a real lack of purposeful behavior altogether. It highlights its critical role in our highest level functions and guiding social conduct.
Okay, delving even deeper into the PFC, there's the dorsolateral prefrontal cortex, DLPFC.
Right. Dorsolateral, if you break it down, dorsal refers to the top, like a fin, and lateral means side. So it's the top side part of the front of your brain.
And what's its job?
It's heavily involved in what we call higher order thinking. Things like sustained attention, your ability to stay focused, and short-term memory, or working memory.
Working memory. That's like the brain's temporary notepad.
That's a perfect analogy. It's where you hold information you're actively working on right now, usually for just about 20 to 30 seconds.
Okay.
What's fascinating and a little sobering about the DLPFC is that it's the last part of the brain to fully develop.
Right, into the 20s.
And it's also the earliest part to show signs of faltering in later life.
Ah, is that why? Sometimes you walk into a room and completely forget why you went in there.
That is precisely the DLPFC having a momentary lapse. It's involved in holding that intention, that task, in mind.
Okay, that makes me feel slightly better.
Laughs. It's a common experience. The DLPFC is crucial for complex problem solving, holding information needed for a task, and it also maintains really rich connections with the hippocampus, the main memory center, helping transfer things for longer-term storage.
Got it. Then there's the orbital frontal cortex, OFC.
Yes, the OFC. It lies just behind the orbits of your eyes, hence the name.
And its role is different from the DLPFC.
It seems to have a closer, more direct relationship with the parts of the brain that process emotions, like the amygdala we'll talk about later. It develops a bit earlier in life and is very closely associated with the social brain.
The social brain, okay. And the classic example here is Phineas Gage.
Ah, yes, the cautionary tale. Phineas Gage was a railway foreman back in the 19th century.
What happened to him?
In a horrific accident, a large iron tamping rod was blown completely through his skull, entering under his cheekbone and exiting through the top of his head. Miraculously, he survived.
Unbelievable.
But the rod specifically destroyed much of his orbital frontal cortex, his OFC.
And his personality changed dramatically.
Completely. His cognitive abilities, his intelligence seemed intact. But his ability to inhibit impulses, to behave appropriately in social situations, was devastated.
So he went from respected supervisor to
unstable, erratic, rude, profane. He couldn't hold a job, eventually ended up as an exhibit in P.T. Barnum's museum, died penniless.
Wow. That's a stark illustration of the OFC's role.
Absolutely. It highlights its profound importance in regulating our emotions, our impulses, our social behavior.
And it's influenced by relationships.
Very much so. The OFC seems to thrive on close, trusting, supportive relationships. Strong bonds appear to enhance its ability to regulate emotions and provide stability.
And unlike the DLPFC, it holds up better with age.
That seems to be the case. The OFC doesn't appear to falter as much in old age, which might be why older adults often remember faces just as well as younger adults do. It suggests an enduring role in social engagement.
Okay, and quickly revisiting the left versus right PFC again.
Right. So the right PFC helps you develop foresight, grasp the gist or overall meaning of the situation. It helps you make plans and stay on course toward the goals.
Understanding metaphors, too, like Michael Phelps is a fish.
Exactly. That requires understanding the bigger picture, the analogy. Your left PFC, in contrast, helps you focus on the details of individual events.
Like specific football scores.
Or precise data points, yes. They both contribute in their unique ways to a comprehensive understanding of the world around you. The detail and the big picture working together.
Okay, moving on from the brain's grand architecture. Let's zoom in even closer now. Let's talk about the social life of those 100 billion neurons.
Laughs, their social life. I like that.
You said earlier they're highly social. What does that mean?
It's not really an exaggeration. Neurons must work with their neighboring neurons. If they become isolated, they essentially wither and die.
Oh.
They need connection.
And their connectivity is just mind-boggling.
Truly. Each single neuron is capable of maintaining connections with about 10,000 other neurons. Imagine the network.
That's astronomical. And what's crucial for our deep dive today is that these connections aren't static, right? They change.
Constantly changing as you learn new things. Whether it's perfecting a tennis swing, learning a new language, or even just figuring out the layout of a new supermarket, every new learning experience physically alters those connections.
How do they actually communicate? It involves chemistry and electricity?
Both, yes. They function on electrical impulses, firing in an on and off manner, but the communication between neurons happens chemically.
Okay.
Neurons send chemical messengers, which we call neurotransmitters,
right,
across a tiny gap between them known as a synapse.
Synapse, that's the junction point.
Exactly. That's the fundamental way one neuron gets another neuron to fire, or sometimes tells it not to fire.
And there are lots of different neurotransmitters.
Over 60 types known so far. Each playing a specific role. Some excite activity, make the next neuron more likely to fire, while others calm it down, make it less likely.
And the synapse itself can change.
Absolutely. The very shape and size of a synapse literally changes as you learn something new. It's the physical manifestation of learning at a microscopic level.
Like remodeling a tiny pathway every time you have a new thought.
That's a great way to visualize it. It's constant remodeling based on activity.
It's like this complex microscopic postal service inside your brain, constantly delivering messages.
Chuckles. That works. And the addresses and delivery routes change based on demand.
Okay, so you mentioned over 60 types, but 2 are the real workhorses.
That's right. 2 neurotransmitters account for about 80% of all the signaling that happens in your brain.
Wow, 80% just from 2. Which ones?
Glutamate and GABA. That's short for gamma-aminobutyric acid.
Glutamate and GABA. Okay, what does glutamate do?
Glutamate is the brain's primary workhorse for excitation. It stirs activity, makes neurons more likely to fire.
So it's like the accelerator.
Pretty much, yes. When glutamate delivers a signal between 2 neurons that maybe weren't strongly connected before, it effectively primes the pump for leader activation.
Making it easier for them to connect next time.
Exactly. And the principle is simple. The more times this connection is activated by glutamate, the stronger the wiring becomes between those neurons. Use strengthens the connection.
Okay, so if glutamate is the accelerator, what's GABA?
GABA is the primary inhibitory neurotransmitter. It does the opposite. It quiets down activity.
Wait, the brakes.
Precisely. It helps you calm down when you need to be calm. It essentially puts the brakes on overactive brain signals, preventing runaway excitation.
Is that related to anxiety?
Very much so. GABA activity is crucial for keeping anxiety in check. In fact, certain anti-anxiety medications like Valium or Ativan work by enhancing the effects of GABA.
Oh, okay. But you don't necessarily need drugs for optimal GABA activity.
Not necessarily, no. Your brain has natural ways to regulate GABA, and lifestyle factors play a big role, which we can maybe touch on later. You need optimal GABA to keep anxiety down.
Good to know. Okay, so glutamate and GABA handle the bulk of the signaling. What about the others? You mentioned neuromodulators.
Right. Though they account for a smaller fraction of the direct neuron-to-neuron firing, these other neurotransmitters, often called neuromodulators, have a truly powerful influence.
Powerful in what way?
They can subtly alter the sensitivity of the receptors on the receiving neuron, making it more or less responsive to glutamate or GABA. They can make a neuron more efficient. They can even tell a neuron to produce more glutamate.
So they're not just hitting the gas or brake, they're fine-tuning the engine.
That's a perfect analogy. They're like the conductors of the brain's orchestra. Sometimes they lower the background noise to bring clarity. Other times they intensify specific signals to sharpen focus or emotional response.
And these are the ones targeted by many modern medications.
Yes, They're widely researched, and many psychiatric medications are designed to influence their levels or effects. Serotonin is probably the most famous example.
Serotonin, definitely heard of that one. Prozac, things like that.
Exactly. Serotonin has attracted significant publicity, partly because of the widespread use of those SSRI antidepressants.
And what's its main role?
It plays a crucial role in regulating emotional tone and many emotional responses. It influences mood, appetite, sleep, anxiety.
Low levels are linked to depression and anxiety.
Is strongly correlated, yes. And also with obsessive-compulsive disorder, OCD. It's often compared to a traffic cop.
A traffic cop? How so?
It helps to keep brain activity under control, preventing things from getting too chaotic or overwhelming, maintaining a kind of emotional balance.
But there's a potential downside mentioned in the source.
Yes, some people on medications that significantly boost serotonin report a kind of emotional blunting. They might say something like, I know that the beauty of that sunset would have had a bigger effect on me in the past, but now I'm sort of numb to things like that.
Like losing some of the highs along with the lows.
Potentially. For some individuals, it suggests a loss of emotional vibrancy or intensity. It's a trade-off some people experience.
Okay. What about norepinephrine?
Norepinephrine plays a vital role in activating attention and arousal. It essentially amplifies the signals that influence perception and motivation.
So it helps you focus, pay attention.
Yes. It turns up the volume on important incoming information, helps you stay alert and engaged.
Also linked to mood.
Yes. Like serotonin, norepinephrine has also been strongly associated with mood regulation and depression. Some antidepressants specifically target norepinephrine, or both serotonin and norepinephrine.
Got it. And the last big one you mentioned, dopamine.
Dopamine, a critically important one. It sharpens and focuses attention, but it's also strongly associated with reward, pleasure, movement, and learning.
The pleasure chemical.
It's definitely one of the principal neurotransmitters that codes pleasure, yes. When you experience something rewarding, dopamine is released, particularly in an area called the nucleus accumbens.
The pleasure center.
It's often called that, yes. This pathway reinforces the behavior that led to the dopamine release, making you want to do it again.
Okay, this is where it gets really interesting, because that sounds like it could be linked to addiction.
Absolutely. When this reward area is frequently and intensely activated, say, by drugs of abuse, or even things like gambling or compulsive shopping, it becomes incredibly hard to stop doing those things.
Because the brain is wired to seek that dopamine hit.
Exactly. It hijacks the brain's natural reward system.
But dopamine isn't just about addiction, right? It helps with focus, too. You mentioned ADHD.
Correct. Medications like Ritalin work by increasing dopamine activity. People with ADHD who take these medications often report not only paying attention better, but also feeling calmer and more focused.
So it helps regulate attention when it's working properly?
Yes. It plays a powerful role in both attention and behavioral regulation. It's all about balance.
Okay, we've talked about the brain's incredible architecture, its chemical messengers. Now let's bring it all together with the core concept that really makes rewiring possible: neuroplasticity.
Yes, the foundation for change.
You said earlier, in the last 20 years or so, there's been overwhelming evidence that those synapses, the communication gaps, they aren't hardwired.
Not at all. They are changing all the time. This dynamic adaptability, the brain's ability to reorganize itself by forming new neural connections throughout life, that's what we mean by synaptic plasticity or neuroplasticity.
The synapses are literally plastic.
Moldable.
Moldable, changeable, constantly being remodeled. That's the key idea.
And this is what makes memory possible.
Absolutely. Your brain literally has to change its synapses when you remember something new. Think about it.
Yeah.
If your brain's connections were fixed, how could it possibly record anything new? It couldn't.
Right. So every time you learn something, remember something.
You are physically creating and strengthening connections between the neurons that encode those ideas, those images, those skills. It's a continuous, active process of rewiring based on your experience.
This perfectly illustrates that phrase, use it or lose it, doesn't it? It really does.
Yeah.
When you actively use the synaptic connections that represent a skill or a memory or a habit, you strengthen them.
And if you don't use them?
Conversely, when you let a skill lie dormant or fail to engage with certain memories, you weaken those connections. It's very much like how your muscles atrophy if you stop exercising them. The brain operates on a similar principle.
Which leads us to that key mantra in neuroscience you mentioned.
Ah, yes. Cells that fire together, wire together.
Fire together, wire together. What does that mean practically?
It aptly describes the way your brain reorganizes when you have new experiences or repeat behaviors.
Hmm.
The more you do something in a particular way.
Like practicing an instrument.
Exactly. Or using words with a specific accent, or practicing a golf swing, or even just thinking about your Aunt Matilda. The more the specific neurons that fire together to make that happen will strengthen their connections. They become more efficient at firing together.
So it's not just a catchy phrase.
Not at all. It's the fundamental principle behind mastering that musical instrument, or eventually remembering your grocery list without even thinking, or driving that familiar commute automatically.
Your brain wires the pathway for efficiency.
Precisely. The more neurons fire together, the more likely they are to fire together in the future. This is how habits are formed, good or bad. Repetition quite literally rewires the brain.
Making things automatic, like learning to ride a bike, eventually it takes less effort.
Exactly. Less conscious effort, less muscular effort, even fewer neurons might be needed eventually because the pathway becomes so efficient and precise.
Okay, so if fire together, wire together explains learning and habit formation, what about forgetting?
Well, just as that phrase became a mantra, so too has an opposite phrase been coined. Neurons that fire apart, wire apart.
Wire apart, wire apart.
It means that neurons that are out of sync, neurons that aren't activated together, will fail to link up strongly, or their existing connections will weaken over time.
So that's the neural explanation for forgetting.
Essentially, yes. It reinforces the use it or lose it principle for forgetting, too. If you don't activate those specific neural pathways, their connections naturally weaken, making it harder to retrieve that information or perform that skill later.
And we have real-world evidence of this neuroplasticity in action, like actual studies showing the brain changing.
Oh, absolutely. Powerful evidence. Take the work of Alvaro Pasqualeone at Harvard with TMS, transcranial magnetic stimulation.
What did he find?
He studied blind individuals who read Braille. Using TMS to map their brains, he found that the brain areas, the cortical maps dedicated to processing sensation from their reading fingers, were significantly larger than the maps for their other fingers, and also larger than the finger maps for sighted readers.
Wow. So the focused use literally expanded that brain region's representation.
Exactly. It vividly shows how cultivated movement and focused sensory input enhance neuroplasticity, physically creating extra processing space in the brain.
Amazing. What about the musicians?
Another great example. Researchers looked at the brains of musicians who play string instruments, like violinists or cellists.
Okay.
For right-handed players, there was no difference in the cortical space for the fingers of their right hand, the bowing hand, but the area devoted to the fingers of the left hand.
The fretting hand, the one doing the complex fingerings.
Precisely. That area showed a dramatic difference. The cortical space dedicated to those fretting fingers was significantly greater in the musicians compared to non-musicians.
And it mattered when they started playing.
Yes. The difference was even more pronounced if the musician had started playing before the age of 12.
So neuroplasticity happens throughout life, but maybe it's more dramatic earlier on.
It seems that way. It definitely occurs in adulthood, but the potential for large-scale reorganization appears greater if the learning starts earlier and is sustained for longer periods. The brain is more adaptable then.
What's even more remarkable, you mentioned earlier, is that it's not just physical behavior that changes the brain.
Right. Just thinking about or imagining particular behaviors can change brain structure as well.
Seriously. Just thinking about playing the piano can rewire things.
The research suggests yes. Studies have shown that simply imagining a session of piano practice contributes to neuroplasticity in the brain areas associated with the finger movements involved in actually playing.
So mental practice isn't just fluff, it actually contributes to rewiring.
It seems to. It demonstrates the immense power of thought on our neural landscape. Your mind isn't just a passenger along for the ride, it's an active architect shaping the structure.
Incredible. Okay, let's unpack this rewiring process even further. What are the specific mechanisms? How does the brain actually strengthen those connections?
One crucial process is called long-term potentiation, or LTP.
LTP, long-term potentiation. Okay.
This is basically how the brain actively strengthens the connections between neurons that are firing together frequently and intensely,
making them more likely to fire together in the future.
Exactly. LTP occurs when the excitation between cells is prolonged. They fired together repeatedly, strongly. This makes them more apt to fire together in the future, creating a change that is relatively long-lasting.
It's not just a fleeting thing.
No, hence the long-term part. It's a physical reorganization to make that pathway more efficient and reliable. Think of it like carving a path in a forest. The more you use it, the deeper and clearer it becomes. LTP is your brain deepening those neural pathways.
Making it easier for signals to travel, for memories or habits to stick.
Precisely. And it involves real electrochemical changes at the synapse.
What kind of changes?
Well, on the sending side of the synapse, the stores of glutamate, that excitatory messenger, get enhanced. More fuel ready to go.
Okay.
And on the receiving side, the receptors for glutamate are reconfigured. They literally change their shape or number to become more receptive, more sensitive to the glutamate signal.
So the message is sent more strongly and received more easily.
Yes. And the electrical voltage on the receiving side might even strengthen in its resting state, which more effectively attracts glutamate when it's released.
Wow. And if this keeps happening...
If this robust firing continues, it gets even more profound. Genes within the neurons can actually get turned on.
Genes?
Yes, genes that instruct the neuron to construct more building blocks for the infrastructure, basically, to build new proteins, new receptors, new structural components to enhance that relationship and make the connection even stronger and more efficient for the long haul. It's like upgrading the communication hardware.
That's amazing. Okay, building on that, you mentioned something earlier, BDNF, brain-derived neurotrophic factor.
Yes, BDNF. Critically important. It's one of the most significant players in both neuroplasticity strengthening connections and neurogenesis, the birth of new neurons.
It's a protein.
It belongs to a family of proteins called neurotrophins that essentially enhance brain cells. It's a huge area of research right now.
And it's nicknamed the brain's miracle grow.
Chuckles. Yeah. Yes, many researchers call it that because of its fertilizer-like functions for neurons.
Like literally.
Well, in lab studies, when BDNF was sprinkled onto neurons growing in a petri dish, they literally sprouted new branches, new connections, dendrites, and axons, much like they do in the brain during active learning and development.
So it promotes growth. How else does it work?
It does its magic in several ways. Inside the cell, it activates genes that increase the production of important proteins, even neurotransmitters like serotonin, and interestingly, more BDNF itself.
So it creates a positive feedback loop.
It can, yes. It also binds to receptors on the outside of the synapse, triggering a flow of ions that increases the electrical voltage, strengthening the connectivity between the neurons.
Okay.
And generally, BDNF helps prevent neuron death, enhances their growth and vitality, and critically, it's activated by glutamate signaling, and it stimulates long-term potentiation, LTP.
So LTP and BDNF are linked?
Very tightly linked. They truly go hand in hand. Researchers have shown that stimulating LTP by learning actually increases BDNF levels in the brain.
And the reverse.
Depriving brains of BDNF causes them to lose their capacity for LTP. So this interconnectedness is absolutely key to how your brain learns, adapts, and grows, reinforcing the strength of those new connections.
Okay, so the brain strengthens connections to learn through LTP and BDNF. But it also needs to forget, right? Or unlearn things.
Absolutely. Just as strengthening is vital, weakening connections is also crucial for adaptation and making space for new learning. This brings us to long-term depression, or LTD.
LTD. Now that sounds bad. Is it related to feeling depressed?
No, not at all. That's a really important clarification. LTD has nothing to do with the emotional state of depression. It's simply the neuroscientific term for the process that weakens synaptic connections.
Oh, good. So LTD helps you unlearn bad habits.
Exactly. Or weaken connections that are simply no longer useful or relevant. It works by literally weakening the connections between the neurons that support an old habit or an outdated piece of information.
Why is that necessary?
This weakening effectively frees up those neurons, makes them available to be recruited into the new, more adaptive connections you're trying to establish with LTP.
Making space for the new wiring.
Precisely. Think about learning a new language as an adult.
Okay.
If you learn it in your 20s or later, you'll likely always have an accent from your first language, right?
Yeah, usually.
That's partly because the neurons that have always connected to make the specific sounds of your native tongue tend to continue firing together strongly, even when you're trying to make different sounds in the new language. LTD hasn't fully weakened those old patterns.
But if you learn younger, say at age 9...
you probably won't have an accent. The brain is more plastic then, and LTD might be more effective at pruning away the interference from the first language's sound patterns as the new ones are learned.
Like the example of parents losing their Boston accent.
Right. If they move away and constantly talk to people without that accent, the neural pathways for the Boston sounds get used less, LTD weakens them, while the pathways for the new accent patterns are strengthened through LTP.
So LTD is crucial for flexibility.
Absolutely. And what's interesting is that when you develop new ideas or insights, the change in your brain, the rewiring, can actually happen much more quickly than changing something deeply ingrained like language or an accent.
Really? Why is that?
It might be because abstract thought involves different, perhaps more flexible neural networks than motor patterns for speech. It highlights the brain's incredible capacity for continuous evolution and adaptation, especially in our thinking.
Okay, moving from those deliberate processes of learning and unlearning, let's talk about the incredible speed of certain brain processes.
Like snap judgments, gut feelings.
Exactly. How do you make those snap decisions or have those sudden insights? Let's turn our attention to some special neurons called spindle cells.
Spindle cells, yes.
Oh.
Also known as von Economo neurons. They are quite unique.
Where are they found?
In large numbers in a few specific brain areas, including a part of the frontal lobe called the anterior cingulate cortex and another area called the insula.
And what's special about them?
What's particularly striking is their potential role in connecting diverse pieces of information very quickly and efficiently, maybe in ways not seen to the same extent in other species.
How so?
Well, the human brain has perhaps 1,000 times more spindle cells than the brains of our closest ape relatives.
1,000 times more. Wow.
Yeah. And many theorists see this as potentially key to our unique human abilities for complex social cognition, intuition, and making those rapid, often adaptive judgments in complex situations.
What do they look like?
They're really distinctive. They have a large bulbous cell body at one end and a very long, thick extension or axon at the other. They look like, well, spindles.
And they're big.
About 4 times larger than typical neurons. Their large size and long shape are thought to enable high-velocity transmission of nerve impulses.
Giving that characteristic snap to a snap judgment.
That's the theory. They seem to provide a critical interface between your thoughts and your emotions. Things like maintaining sustained attention, self-control, and crucially, giving you the flexibility to make quick but complex problem-solving decisions, especially in emotionally stirring situations.
And they connect important areas.
Yes, they have rich receptors for key neuromodulators like dopamine, serotonin, and vasopressin. And they form connections between that cingulate cortex and the orbital frontal cortex, the social brain area we discussed. This highlights their importance in social relatedness, emotion regulation, and perhaps even how therapy works by integrating thought and feeling.
But these spindle cells, they don't work in a vacuum, right? They need existing networks.
Absolutely. They can't do their magic out of thin air. They rely on the existing neural nets that you've already built through learning and experience.
So you have to lay the groundwork first.
Yes. Snap judgments and insights seem to involve the spindle cells rapidly integrating information from the neural nets you've already formed through slower learning processes like LTP. They weave together existing knowledge in novel ways very quickly.
Let's use that Hurricane Katrina example from the source to illustrate.
Right, that's a powerful one. Imagine you're driving, heading to New Orleans for a planned vacation.
Okay.
You hear a radio report. Hurricane Katrina is bearing down, about to hit the city. What happens next?
Panic, reroute.
Probably both. Your spindle cells might kick into high gear, integrating the threat information, your travel plans, emotional responses, and you make a snap decision, likely without much conscious deliberation, to immediately reroute, maybe head towards Houston instead.
Okay, makes sense. Fast decision under pressure.
Then, once you're in Houston, you hear that hundreds of evacuees from Katrina are being sent to the Astrodome.
Yeah.
So maybe another snap decision happens. You spontaneously decide to spend part of your vacation time volunteering in a soup kitchen set up there.
Based on empathy, available information.
Exactly. These were all rapid decisions made in complex, novel, and emotionally charged circumstances, likely relying on spindle cells, quickly integrating diverse information streams and your underlying values.
And years later, that vacation might feel really meaningful.
It might be viewed as one of your most rewarding experiences. Now, here's the ongoing rewiring part. Every time you remember that story, certain synaptic connections related to it are strengthened, while others might be weakened based on the details you recall and emphasize.
So recalling the memory changes it.
Subtly, yes. As you discuss the events with friends, maybe they talk about the government's response or the resilience of the evacuees. Other synaptic connections get made with those original memories, influencing your perception and the emotional tone.
So you're essentially rewiring the memory trace every time you revisit it.
Pretty much. You're adjusting its neural representation based on new inputs, reflections, and the context in which you remember it. The story and your brain's version of it evolves.
Fascinating. Okay, moving on to another critical aspect. The emotional core of memory, deep inside the brain.
Yes. Down in the temporal lobes, nestled deep inside, are two crucial structures intimately involved in memory, often in very different ways.
The amygdala and the hippocampus.
That's them, the dynamic duo of memory and emotion.
Let's start with the amygdala. What's its role?
The amygdala, its name, comes from the Greek word amygdalon for almond. Because of its shape, is primarily your brain's emotion processor, especially for intense states like fear and threat.
So it's the alarm system.
It acts very much like a rapid alarm system, yes. It gets triggered quickly and assigns emotional intensity or significance to incoming sensory information.
Like that panic button you mentioned earlier.
Exactly. It often serves as that primal panic button. It can be triggered instantly by potential threats, but also by socially significant stimuli. Like maybe a quick glance from an attractive person that makes your heart race, or even your boss glaring at you across the room, triggering a jolt of anxiety.
So it makes immediate emotional assessments.
Very immediate. It illustrates its role in rapid, often unconscious, emotional appraisal of stimuli, driving our fight-or-flight responses sometimes before our conscious brain even catches up. Understanding this is key for managing fear and anxiety.
Okay, then there's the hippocampus, also named for its shape.
Yes. Hippocampus is Greek for seahorse, which it vaguely resembles with its curved shape.
And its role is different from the amygdala's.
Very different, though they work together closely. The hippocampus is absolutely critical for forming new explicit memories.
Explicit memories, like facts and events.
Exactly. Memories that you can consciously recall and declare, like what you had for breakfast, or the capital of France. The hippocampus is essential for encoding these.
And this is where that neurogenesis happens, the birth of new neurons.
Yes. Researchers made the truly critical discovery relatively recently in neuroscience terms that neurogenesis does occur in the adult human hippocampus.
Which was thought impossible before.
For many years, yes. The dogma was that you were born with all the neurons you'd ever have, especially in areas like the hippocampus.
So this discovery is huge.
It's massive. Because it means this part of the brain, crucial for laying down new memories, retains the ability to generate new cells throughout life. It highlights the profound importance of things that support hippocampal health, like learning, exercise, stress management, for literally rewiring your brain and enhancing its capacity for new learning and recall.
So the hippocampus handles the what, where, when of memory, and the amygdala adds the emotional color or tag.
That's a good way to think about it.
Right.
The amygdala tags memories with emotional significance, which actually helps the hippocampus consolidate them more strongly, especially if the emotion is intense. That's why you remember highly emotional events, good or bad, much more vividly than mundane ones. They work in concert. The hippocampus is more involved in explicit memory, the amygdala more in implicit emotional memory and associations.
Okay, wow. We've covered a lot of ground about the brain's inner workings.
We have indeed, from the big picture down to the microscopic level.
So what does this all mean for you, listening right now? We've unpacked these incredible details, the architecture, the chemistry, the amazing adaptability. Now let's bring it back home. How can you actively apply this knowledge to intentionally rewire your life, as Dr. Arden outlines?
Yes, this is where the rubber meets the road. This isn't just fascinating theory. It's a blueprint for tangible change.
And this deep dive, the whole point was providing those detailed, easy-to-understand explanations of these principles.
So you feel empowered to make those changes in your own life. We've laid the scientific groundwork, and now it's about connecting those dots to practical, actionable strategies.
Things that can make a real difference starting today.
Exactly.
Okay, first up, cultivating good habits and quieting fear. Let's circle back to cells that fire together, wire together.
The core principle.
The insight here seems to be if you want to build mental connections that support good habits and actively weaken those supporting bad ones, the mechanism is repetition and focused attention.
Yes, it. Consistent practice strengthens the desired pathway.
Dr. Arden uses that acronym FEED, right, to help remember the steps to feed your brain for this rewiring.
Yes, FEED.
Yep.
It stands for focus, effort, effortlessness, and determination.
Focus, effort, effortlessness, determination. Can you break that down quickly?
Sure. Focus means paying close attention to what you want to change or learn. Effort is the initial work required to practice the new thought or behavior. Effortlessness is the stage where, with enough practice, it starts to feel more automatic. The wiring is strengthening. And determination is about sticking with it, especially when it feels hard, reinforcing the commitment to change.
So it's an active, consistent process guiding the brain's changes.
Very much so. You're actively participating in the rewiring.
And connecting this to taming the amygdala, quieting that panic button.
Yes. It's not about eliminating fear entirely. That's impossible and not even desirable. Fear serves a purpose. It's about learning to put the amygdala's initial alarm reaction in check with your prefrontal cortex, your executive control center.
Bringing the thinking brain online to modulate the emotional brain.
Exactly. And a key insight, a practical technique, is simply naming the emotion you're experiencing when you feel that surge of fear or anxiety.
Just saying, I'm feeling anxious.
Yes. Saying to yourself, okay, I'm feeling anxious about this presentation, or I'm feeling angry right now. That simple act of labeling the emotion actually activates your prefrontal cortex.
And that dampens the amygdala?
It can immediately begin to reduce the amygdala's panic button response. It's like engaging your rational executive to acknowledge and manage the emotional alarm system rather than just being swept away by it.
That's powerful. What about the nervous system balance? Sympathetic, parasympathetic?
Understanding that is also crucial. Your sympathetic system is the fight-or-flight accelerator. Your parasympathetic is the rest and digest brake. Often, anxiety involves an overactive sympathetic system.
So how do you apply the brakes?
Consciously taking a few slow, deep breaths, especially making the exhale longer than the inhale, directly activates your parasympathetic system.
Just breathing differently.
Yes. It sends a direct physiological signal to your brain to calm down after activation. It helps you turn off those false alarms triggered by the amygdala and approach situations more courageously, rather than being constantly hijacked by fear.
Simple, but sounds effective. Okay, what about boosting mood and memory? How does neuroscience help there?
Well, we know that activity in the left prefrontal cortex is generally associated with more positive emotions, while the right PFC can be more active during negative states. So intentionally shifting left can help alleviate depression and promote positive feelings.
How do you shift left?
Through techniques like behavioral activation. This involves scheduling and engaging in activities that, historically brought you pleasure or a sense of accomplishment.
Even if you don't feel like doing them right now.
Especially then. Even small positive actions can jumpstart those positive neural pathways in the left PFC. Another technique is cognitive restructuring.
Challenging negative thoughts.
Exactly. Learning to identify, challenge, and reframe those automatic negative thought patterns literally rewires the way your brain processes information, making it more balanced and optimistic over time.
And even simple things like light exposure matter?
Yes, getting sufficient natural light, especially in the morning, has a direct impact on your brain's biochemistry, including serotonin levels, which significantly affects mood.
Okay, and for memory, applying neuroplasticity.
The key insight for memory is to make new information sticky by actively working with it and connecting it to what you already know.
Creating richer connections.
Exactly. Instead of just passively reading something, actively try to explain it in your own words, think of examples, or relate it to your own experiences. Using mnemonic devices, acronyms, rhymes, visual imagery also creates multiple pathways to the information.
Like linking items on a grocery list to locations in your house.
Perfect example. Or using spaced repetition, reviewing new information at increasing intervals over time. This directly engages LTP and strengthens those synaptic connections, enhancing your brain's fundamental ability to encode and retrieve information efficiently. You're actively cultivating your memory skills.
Beyond the mental techniques, what about the brain's physical needs? Fuel and maintenance.
Absolutely crucial. Your brain fundamentally needs the right biochemical environment to perform optimally and facilitate all this rewiring.
Nutrition is key.
Foundational. You need the right building blocks, amino acids from protein, essential vitamins, minerals for neurotransmitter production, and overall cell function.
And fats. I hear about omega-3s.
Essential fatty acids, particularly omega-3s found in things like fish oil, flax seeds, walnuts, are incredibly important. They make up a significant part of your neuronal membranes.
Why does that matter?
Flexible, supple cell membranes are critical for neuroplasticity. They allow the receptors to move and change shape, enabling synapses to adapt and learn. Rigid membranes hinder this dynamic process. So good fats literally make your brain more adaptable.
Wow. Okay, what about exercise and sleep? We always hear they're important.
Their role in rewiring and brain health is significant, perhaps even more than people realize. Exercise, especially aerobic exercise, is arguably one of the most powerful ways to jumpstart the neurochemical mechanisms of both neuroplasticity and neurogenesis.
How?
It increases blood flow to the brain, delivering more oxygen and nutrients. Crucially, it boosts levels of BDNF that Miracle-Gro we talked about, directly supporting the growth of new connections and even new neurons, particularly in the hippocampus.
So exercise literally helps your brain grow and learn better.
The evidence strongly suggests yes. And sleep, it's absolutely vital.
Not just for feeling rested.
Far more than that. Sleep is critical for memory consolidation. During certain stages of sleep, your brain appears to replay and strengthen the new neural connections formed during the day, essentially solidifying learning and integrating new information.
So pulling an all-nighter to study is counterproductive.
Terribly counterproductive for long-term retention, yes. Sleep also plays a huge role in emotional regulation and allows the brain to perform essential maintenance, like clearing out metabolic waste products that accumulate during waking hours. Consistent, quality sleep is non-negotiable for optimal brain function and rewiring.
And you mentioned psychoneuroimmunology. That sounds complex.
It just refers to the field studying the intricate links between your mind, your brain, and nervous system, and your immune system, immunology.
How are they connected?
Profoundly. Your thoughts and emotions directly influence your nervous system, which in turn influences your immune function and vice versa. Chronic stress, for example, can suppress immunity. Positive emotional states can bolster it. It highlights the holistic nature of health. Mind and body are deeply interconnected, influencing brain health and resilience.
Okay, what about relationships? How does rewiring connect to our social lives?
The concept of the social brain is key here. We have specific brain systems that are geared towards understanding and interacting with others.
Like mirror neurons.
Mirror neurons, which fire both when we perform an action and when we see someone else perform it, are thought to be involved in empathy and understanding others' intentions. Also, those spindle cells we discussed, the orbital frontal cortex, the anterior cingulates, these are all parts of the network enabling empathy, social bonding, and navigating complex social situations.
And the research shows good relationships are good for us.
Overwhelmingly so. The key insight is consistent across studies. People who maintain positive, trusting social relationships tend to live longer, are physically healthier, and report greater life satisfaction. Social connection is a fundamental human need with deep biological roots.
So how can we actively use this?
By consciously practicing empathy, really trying to step in someone else's shoes and understand their perspective. This actively engages your mirror neuron system and strengthens social circuits. Building and nurturing supportive relationships literally strengthens the parts of your brain involved in well-being.
And resilience, bouncing back from challenges.
Yes, rewiring can increase resilience. You can learn to approach life with vitality despite obstacles. Part of this involves maximizing your brain's capacity to see the bigger picture, which often strengthens with age and experience if cultivated.
Using positive psychology ideas.
Exactly. Drawing on concepts like cultivating optimism, which is learnable, setting healthy, meaningful ambitions, and practicing compassion, both for others and yourself, and a degree of non-attachment, acceptance of life's bumps. These practices help you navigate challenges with more flexibility and lift distress, literally rewiring your brain to be more resilient.
And finally, tying a lot of this together, the mindful attitude.
Yes. The key insight here is the calming yet vitalizing role of attention, which is largely governed by your prefrontal cortex, and how directing your attention shapes your overall attitude and experience.
Through things like meditation.
Meditation particularly practices focusing on breath or body sensations. Parasympathetic meditation is a direct way to train your attention and intentionally engage your parasympathetic nervous system.
Shifting away from the stress response.
Precisely. This can, over time, increase your tolerance for stress and cultivate a more fundamental underlying sense of peace and stability, even amidst external chaos.
So the goal is being more present.
Yes. Consistently increasing your ability to be mindfully present, truly engaged in the current moment without excessive judgment or distraction, and fostering a sense of connection, both internally and with others, and the world around you. This allows your rewired brain, your whole self, to operate at its most harmonious and effective level, fostering profound well-being.
So, wrapping this all up, what does this really mean? Our deep dive today, it seems to have revealed this profound truth. Your brain isn't static. You're not just a product of your genes or your past.
Not at all. Instead, your brain is this dynamically changing, adapting, transforming entity.
Constantly being sculpted by, well, by everything. Experiences, thoughts, actions.
Exactly. That image of tangled wires inside the brain, which might seem overwhelming at first.
Yeah.
It actually represents an incredible truth. Those wires are constantly being rewoven, reshaped, refined, and importantly, you are involved in that process.
Right. And this deep dive was really about providing those details, those easy-to-understand explanations to empower that capacity for change.
To give you the knowledge and the tools.
So this raises a really important, maybe even provocative question for you to ponder as you go about your day. If every single thought you have, every choice you make, every habit you engage in is quite literally physically reshaping the architecture of your brain, what kind of architect do you choose to be for your own mind?
That's the ultimate question, isn't it? The power to build a calmer, more positive, more resilient you. It's quite literally right there inside your head, waiting to be guided.